who can help us? What is stereoscopic parallax? What does it mean? What does it, if you don't know what it is, then I think we can help you. But if you don't know, we can just also move on as well. What is stereoscopic parallax? Yes, anyone? What's stereoscopic parallax? I'm left with Jonathan. The rest have dropped off. Bad network. I'll tell you, people, buy Vodafone. If you want to do anything online, Zoom and all these things, Vodafone is so far, I think is the best. You see, I'm using Vodafone right now. Okay, anyway, so what is stereoscopic parallax? What is a stereoscope? I think most of you have used stereoscope before. What was it about? What was it about? What was it used for? Or you are not going to talking to me? Okay, your network is bad. All right, so let me carry on then. I won't waste time trying to explain a lot of things or get your understanding. I want it to be interactive, but if I won't get a response, I think I'll move on. So later on, I won't be blamed. Are you okay? So parallax itself is apparent shift in position of an object. Apparent shifts. Apparent, the opposite of apparent is real. So it means that someone said apparent shift, it means the thing hasn't really shifted, but it looks to you that it shifted. So in reality, there was no shift. Okay, so apparent shift in the position of an object with respect to the frame of reference caused by the shifting in the position of the observation. Okay, so here, this is English language all mixed up nicely for you in a cocktail of a definition. So the shift should be with respect to a frame of reference. Let me tell you, the long and short of this definition is that when you actually move, sometimes objects seem to move as well. And it's quite a confusing phenomenon, but it happens. Are you okay? So when you travel and you sit in a car to travel from Kumasi to Accra to Tamale, wherever it is, when you sit on an aeroplane, when you actually move, sometimes objects tend to also move, okay, with reference to a certain framework. The framework could be, a window that you are looking through. Are you okay? So something seems to be moving, but there's another thing that's stationary, and that's the reference framework, the reference frame, or a frame of reference. So parallax is interesting, and I experienced parallax when I traveled to Inzolenzo for the first time. I went to work in the Western region, and a friend said we should go there, and we went there to sit on a boat, isn't it? Not a ship. And we went to the village. So someone was paddling the canoe, and as we approached the village, it was interesting. You could see that we were really rowing the boat against the flow direction of the stream. And that was quite, the guy had to be strong enough to paddle against it to get us across. Okay, so if you don't have experience, then it's going to shift you. But that's not my focus. I want you to draw your attention to something that I observed, and I think a lot of people observed it. And as you approach the village, all the structures they build, they tend to move. You literally see it moving. It's like almost scary, So that is parallax. What you observe there is what we call parallax. When an object moves, but doesn't really move, but it seems to you that it's moving. So when you sit in the car and you see the trees moving, as if the trees at the back are kind of speeding. They are really moving very fast. That sort of thing is called parallax. So it's apparent. No trees moving anywhere. To you, there's a tree moving. So parallax is the apparent shift in the position of an object with respect to a frame of reference. And this apparent shift is caused by the shift in the position of the observation. So the observation is the person who is looking at it. So you cannot experience parallax for someone. It's got to be you. Okay. But let me tell you the secret for talking about this. The reason that we talk about this is because we want to take advantage of that phenomenon and develop a theory, a concept. Are you okay? If we're going to develop what we call the parallax equations, and the parallax equations will relate the various position of objects on the two photographs, okay, to their height, the height of the actual object on the ground. Okay, so parallax is interesting. I just love talking about parallax all the time. I'll be very happy to always talk about it because I realize that for someone to sit down like this and think about a theory like this, that's fantastic. A few things to observe: changing the position of an image from one photo to the next is caused by the aircraft's motion. But what are we saying? What we are saying is that when an aircraft takes a photograph at the so-called, not the so-called, I like using that phrase so-called, but I think I'm abusing the use of it. The exposure station that we talked about in the previous lecture is the position of the front or the rear nodal point. Are you okay? In terms of ground coordinates, in other words, the location of the aircraft at the point where the exposure was made, at the point where the picture was taken. That is what we call the exposure station. Now, so when we actually take that the first exposure, the first photo, and we take the second one, objects don't remain where they are with regards to the frame of reference, which is actually the actual photographic extent. The photograph itself becomes a frame of reference. And when you look at the photo 1 and look at photo 2, you realize that the objects they're not at the same place. They seem to have shifted from where they are. Okay, so that is parallax. That is parallax. So how can we proceed? We can only proceed this way. We can proceed by just saying that, okay, if that is parallax, then the same parallax we're experiencing, we're having the same thing happening here. So stereoscopic parallax is leading us to stereoscopic parallax. Okay, all right. Parallax of any point is directly related to the elevation of the point. So objects that are closer tend to move faster. When you sit in it, always remember that when you sit in a car, the trees that are closer seem to be speeding very fast as you go, as compared to the trees that are farther away, if we actually look through the window. So parallax has a direct relationship with the elevation. What is the elevation? Here, I think I want to bring your attention to something. When you drive and look through the window, the distance of the tree from where you are in the car, that distance, when you turn it upside down like that, and then you will be in the sky, like you'll be the camera, your eyes are the camera, and the camera is looking at objects down. The distance of objects from down in the vertical, along the vertical, is called elevation. So you can see that the parallax you experience on the ground is synonymous with the parallax or what we have in the case of having multiple exposures in terms of photogrammetry. Parallax is greater for high points than for low points. So like I said, because the objects seem to be moving faster that are closer to you, it means Objects that are closer to you are actually what? High points. I get that. And then objects that are farther away are low points. That's if you reverse the whole thing like that. So I'm driving. This is me. These are trees, and they seem to be moving faster if they are closer. But if they are farther away, they are slow. You know, they don't really move fast. That means parallax is small. But if I turn it this way, you can see that objects that are closer to me have higher elevation. Are you okay? All right. My lecturers taught me when I was learning some of these courses by using their hands, the way I'm doing it. It's like you're conducting music, but anyway, who cares? As long as you understand it, I think that's the most important thing. So these are the two important things to aspects of stereoscopic parallax. So parallax, we can actually forget about the sweet story about parallax and start looking at it mathematically. Are you okay? So mathematically, parallax is simply PA equal to XA minus XA prime. All right. So here, the first thing to understand is your coordinate system, the photographic coordinate system. I think we talked about it, but I like to repeat. And you know, if I like to repeat, then it means that it's important to me, isn't it? So you have the first exposure and the second exposure. Then there's an overlap. Are you okay? All right. So in your first exposure, you have an object, the same object. It has to be the same object. So somewhere here and it has to fall within the overlap region, and they get recorded. So we drop a vertical and we drop a vertical here. So they have to, a point A, which is actually on the terrain, gets captured twice. All right, so it gets captured here and it gets captured there. Okay, now what does it mean? It actually means that the object could be a coconut tree, the corner, the intersection of a road could be, you know, the intersection of some walkway, footpath, okay, will appear, or the corner of a building will appear twice. They will appear here and there. So appear here and there, two locations. All right, so if you have an object appearing in two locations, it only means one thing. It means that you have, if you put up the photograph like that, okay, so let's have the developed photographs. Then the object will appear in two different locations on the photograph. One will appear somewhere here. The same object will appear, will have two images with two different locations. The other will appear somewhere there. It's like as if it's disappearing. The objects are disappearing off the photograph. The images of an object, as we move from left to right, because the flight direction is this way. Are you okay? The flight direction is this way. You fly from left to right in photogrammetry. All right, so what does it mean? It actually means that two different coordinates. So parallax is just finding the change in the coordinates. Are you okay? So the S coordinate is actually from, is measured along the X axis. Okay, so X okay, so X is measured this way. All right, and you can see that XA is also going to be this, the center of the photographic coordinate system, the photo coordinate system. So we have fiducial coordinate system, photo coordinate system. Are you okay? All right. And so we can have XA, XA prime, And then parallax is the difference between the two, xa minus xa prime. Okay, so we can go back to our presentation. All right, and then here what we're trying to do is to make it exaggerate a bit everything that is happening up here. We're trying to exaggerate everything here. I want to actually combine the two in this diagram here. So everything you find in this diagram is actually these two similar triangles that are being combined. So you can see L1, L2 at the same location. So that we've done a superimposition, okay, superimposition or an overlay of the two. All right, now when we do that, it helps us to appreciate the coordinates very well. Okay, so for a point A on the ground, we have the coordinates to be A and then A prime. Okay, so typically, in the way my friend Mr. Ochre actually pronounces the word typically, we have A prime here, then we have A there. Okay, so that is actually this line here, but then we cut it short. Again, that we don't bring it, so we are looking at it, the short version of it. All right, and then we are looking at A, so you can see that now the object is getting close to the center. It's going to the left. Object seems to disappear and move to the left. And we simply saying that PA equal to XA minus XA prime. What it actually means is that we can also write PB equal to PB XB minus XB prime. Okay, and that will be the parallax for point B. So we know parallax for point A, and we know the parallax for point B, and for point C, and for D, and E, F, G, H, I, J, K, all sort of possible points that we can have, the thousands of points that are possible on a photograph. We can find their parallax by simply identifying their conjugate point. In other words, finding points that are similar to them. Okay, so we find the same objects, all right, the image of the same objects on the photographs. We'll be working on the parallax, simple as that. Okay, so moving forward, where are we? So parallax measured in fly line axis. Yes, obviously. Yeah, we can look at that one. Okay, let's move on. There seems to be slight difference between the fly path and the actual x-axis. Okay, it seems to be tangential to it. All right, monoscopic parallax. So we differentiate between monoscopic parallax and then stereoscopic parallax. Okay. All right, so I had a meeting at 2 o'clock. I don't know if the meeting started or not. And you guys just surprised me. I don't know when the time is for this one, but let's do this. Let's do it. All right, so monoscopic parallax measurements, that means that you are using just one, you're looking at one photograph. You're actually not considering the two. So normally that's what monoscopic means, one. Stereoscopic means two. Is that okay? All right. So if you take this one, very simple exercise. You take two photographs. You measure the distance between the two principal points, and that is D. I get that. And then when you take D and you actually measure the distance between any two conjugate points, you end up having what? The parallax for the points. Are you okay? All right. Okay. So you have to, of course, the procedure is to mark the principal points, align the fly line axis. Are you okay? And then you can now calculate the parallax. Okay, so that is how monoscopic parallax is done. Now remember that it could be, you could have it in units, centimeters, millimeters, inches. It depends on if you're in America. It doesn't matter. The most important thing, knowing your units, start from primary school, class 3. You start learning millimeters, how many millimeters make, are you with me, a centimeter, etc. That has nothing to do with what we're talking about. You have to fix yourself. Don't fix the country. Anyway, so this one, like I said, you need to know those things for yourself. All right, stereoscopic parallax. Before we talk about that, the principle of the floating mark. So the principle of the floating mark is actually, is kind of elusive. In other words, we try to do something, view in stereo, are you okay, by placing two identical marks which have been etched. When I say etched, it's been permanently marked, are you okay, on clear glass. Okay, on clear glass, and those marks are called a half marks, and the half marks are shifted until they fuse into a single mark. What does it mean? If they fuse into a single mark, then it means that you've actually achieved a model. Are you okay? A fused model. I don't know how to put it, but what it means is that you are looking at something from the left and from the right in such a way that your eye basis represents the position at which those images were taken. Is that okay? If the marks move closer, they appear to rise. Why not? Because there's parallax. Are you okay? Okay, so, and of course, the space of the half marks and the parallax are varied so that floating marks appear to rest exactly on the terrain. So you see, when you look at a 3D model, by observing two photographs, you tend to have a three-dimensional impression of the terrain. And that's what we're talking about. Okay. So there you go, parallax of the principal point. What is the parallax of the principal point? The parallax of the left ground principal point is the photo base measured on the right photo. I mean, this one is, if you don't use wisdom, you won't appreciate it. Is that okay? Because the principal point doesn't really have any distance that it can move. Are you okay? But the representation of the principal point on another photograph and the distance between the principal point on that photograph and the other one, the other principal point, becomes the parallax. Okay, so the parallax then becomes the B, which is, B is really the photo base. It's the distance between the two exposure stations, the photo base. Okay, so the center of the photograph of photograph one, photo one, okay, can appear, the pic, whatever is there, if it's a building that is close to that place, it will appear in another photograph. So if you're able to identify it, you can get the photo base, which is the distance between the two photos. All right, now we come to the stereoscopic parallax. How do we measure parallax without considering the two photographs? How can we do that? We make use of the parallax bar. So what you see on there is the parallax bar, and K is a parallax constant, RA is the reading to any point. Okay. All right, and there's a movable half mark. Okay. So this is a measuring instrument. There's a fixed half mark that you put on a conjugate point. So to find the parallax between 2 points, you simply put a fixed one on 1 point and identify the conjugate, and then place the movable half mark, adjust it so that it falls there. Then you can use an equation to determine the parallax. Okay, so you can come out with this. PA which is the parallax at a point, is actually a constant c plus the reading there. Okay, so which means that you can simply use that constant to now just read the value to any point and then tell the parallax there. I mean, simple as that. Okay. Now we come into the parallax equations. So the parallax equations, we go straight to them. We don't have to go to the derivation, and it's not necessary. But you can understand the concept well if you actually look at the derivation. You appreciate the diagram. So here we go. The parallax equations, here they are. But you need to appreciate them. You need to, for any point of height h above the datum, yeah, we can establish that h is equal to the flying height minus the air base, capital B, times focal length, okay, and then over the parallax. Okay.
Recording in progress.
All right, so we have that equation on top. I mean, it's as simple as that. There's nothing more we are going to do. Okay. There's nothing more we're going to do than just understand. Okay. Let's understand the equation and the parts of the equation. Okay. All right. So look at it carefully. This is another equation that we have. Capital X, which is really a ground coordinate. When you see capital X, a ground coordinate, is equal to the air base B. The air base is the distance between the two exposure stations. Okay. And then times the photo coordinate X. Okay. So S equal to BX over P. Put that in your head. S equal to B, capital X equal to BX over P. Okay. Capital X equal to BX over P. All right. So let's go to the whiteboard so that I can probably do this for you. Okay, we have 10 minutes. When the 10 minutes expires, please rejoin. Kindly rejoin. All right. So if we actually shift it up and then write big X equal to BX over P. All right, what we actually saying is this, that for any point A, this is what I want the student to note. The formulas are not the way they are written. Okay, they are slightly, you have to adapt it. So X capital A for any point A. So normally we ask a question to calculate for X at a certain point. You have to adapt the formula to look like this. Let's say over PA. So the parallax at point A, XA, are you getting that? Okay. So parallax for a particular point. All right. Parallax at a particular point. All right. Should be looked at this way. Okay. So you adapt it. All right. So there you go. Let's go back and look at this one too. So smaller h equals to h minus bf over p. All right. So if you actually put that in your head and we go back there on the board. Okay, so this is what you do. Small h, you have to adapt it, subscript A. So a point A having an elevation of A is equal to bigger H minus BF over P. All right. So here to remember that subscript A for the point A so you have subscript A, focal length is F, is fixed. Then so what is H? H is the flying height. Again, that is to flying height. All right, so here we go. Let's move on. So x equal to bx over p. We can also say y equal to by over p. These are the parallax equations. So with this, you can solve problems. We can start solving problems. So parallax equations, here you go. They are valid for truly vertical photographs only. So you can apply parallax equations to tilted photographs. Forget about it, it won't work. Photos taken from the same flying height. So you don't take one photo is down, the other is up. Are you with me? Like, not the photo itself, but the exposure stations. Okay. So coordinates are related to the flight line axis system. So when you say X, capital X, you're not referring to the plane coordinates but being used, are you okay, by Lands Commission, are you okay? Ground coordinates are not related to the true ground coordinates, but to the coordinate system of the stereo plane. All right. So remember that there are different coordinate systems. There are different coordinate systems. Okay. Elevation by, so we can divide a new formula. Elevation by parallax. Okay. Okay, so that can also yield, if you prove it, we can have this nice, beautiful formula. So let's take note of the formulas that are important in photogrammetry 1. Sometimes I don't know what you can do about equations. You simply put it in your head, memorize it. Are you okay? Nothing more. So we've learned the 3 parallax equations, capital X equal to bx over p, capital Y, by over p. Then the height one, small h equal to big H minus b p over bf over p. All right, so this is a new one, but here we are considering 2 points. So parallax differences. So remember that parallax of a point is a difference between the coordinates, but parallax differences is the difference of differences of coordinates. You get that? In other words, you are doing delta p. Okay, delta p here is actually the change in parallax between point A and point C. Change in coordinate between point A and then point C. Is that okay? So here we go. You can use this formula. Okay. All right. So that is basically it. It's worth taking note of that. Ground principal points. Like we said, for the ground principal points, the parallax there is actually the same as the base, the photo base. All right. So anytime you hear ground, just assume it. All right. So we can write more equations. So basically, that is that. Okay, we're not putting any examples, but if you were in the last class, working an example for this should be easy. You know your flying height, you know your focal length. Are you with me? You are given a photo coordinate. Why can't you work out? Are you okay? Make it the subject of the equation. So let's move on. If you have any question, you can actually ask, but I think we're not doing any calculation on this one. We are not working an example on this one. That's what I want to say. Okay. All right. So there we go. Any question, please ask your questions if you have a question. Thanks, Manda, for the opportunity. If you have a question, let us have it, please. Do you have a question? Do you understand the concept? So if I ask you a question, you can work it out. If I ask you a question on parallax, can we get it? Okay, so you're not going to mind me as usual. I think you are proud of that, aren't you? Are you okay? Okay, but the good news is that I should have talked about stereoscopic viewing before I talk about stereoscopic parallax. So if you understand stereoscopic parallax, then it means everything I'm showing on the board is just easy peasy for you, because stereoscopic viewing is a requisite knowledge. You require it to be able to understand stereoscopic parallax. So like as the name goes, view with two eyes. Are you okay? All right. So if I'm sharing my PowerPoint, we can have, I'll brush through this quickly. So we have binocular vision, then we have monocular vision, with viewing with one eye, viewing with two eyes. There's depth perception. Okay, so I was talking about depth, remember? Depth is how far something is, how deep something is. Are you okay? All right, so how do we perceive that? We use shadows, hidden objects. Are you okay? When you use just one eye, you can only see something as far away if it is covered by something. So if your sister is standing in front of you,